Hello everyone, welcome to another lecture of control system. In today's class, we are going to see about the root characteristics of your second order overdamped system. So what is an overdamped system? It is a system where my zeta is greater than 1. So we're going to look how the transfer function of your overdamped systems is going to be. Then what are the roots for the characteristic equations of that overdamped system, followed by what is the step response of such an overdamped system. So overdamped system is a system where you are having the zeta greater than 1, and that is something of a botheration because your roots are going to be just along a single axis. So we're going to see about that. So let us take our transfer function to be C of S to be C of S upon R of S, and that is going to equate to omega n square divided by s square plus 2 zeta omega ns plus omega n square. Now the roots of my denominator. So the roots of my denominator can be written from our previous classes as a quadratic factorization, and that's going to come out to be minus zeta omega n plus or minus omega n root of zeta square minus 1. So now I can tell about S1 and S2 is that what I can say is when zeta is greater than 1, neither of my S1 and S2 roots are going to be imaginary, are going to be complex and imaginary. They are going to be real roots, right? So they are going to have real values and they can be either. So let us say my omega n is fixed. So my minus zeta omega n plus or minus omega n is going to place the root on either the right side or the left side of the S-plane real axis. So the roots are basically, I will just say at this point I can say that the roots are real, and it doesn't have we are only, whereas your underdamped system we were able to work the entire quadrant, right? So here we are not, it's only the roots are only on your real axis because the roots are real and the imaginary value is equal to 0. So how do we solve this? Now I'm going to use, instead of that big roots on the right hand side, I'm going to just stick to my S1 and S2, and then I'm going to do the partial fraction expansion and then inverse compatibility, and then after that I can put back my S1 and S2 and study how the step response is going to be for this second order system, which is overdamped with zeta greater than 1. So let's see how do so the steps from here onwards are pretty much the same that we have seen in our part 1 and 2. So I'm going to do my partial fraction expansion, a by s plus b by s plus 1 plus c by s plus 2, and that is going to be, you need to multiply your RHS and LHS with the denominator of the LHS. So that is gonna take my fractional terms and then give me a non-fractional equation. From there I can equate the coefficients of s square, s to the power of 1, s to the power of 0, and then I'm going to find my ABC. So let's get to it. So simply s plus 1 and s plus 2 I'm multiplying. So I'll be cancelling out a few terms. So now the point I want to mention here is, for an overdamped system what we can say is the roots are just real and then they occupy the real axis. So because I am having my S-plane to be between, my y-axis to be imaginary and my x-axis to be real. And in this case, for an overdamped system, what happens is your roots are occupying the real axis, and it is, it can either be on the negative side, or it can be, it can be on the right side of the real plane, or it can be on the left side. So on the real axis, the imaginary axis is on the center, right? So, just I'll say that it's not a system that we are very fond of in our designs, where you have the roots occupy just a straight line in your S-plane, right? So you want to work with the whole quadrant. You want to work with all the 4 quadrants. You want much more room for your roots to occupy, so that your systems can have more flexibility in your designs. So that is why we are not very particular about this overdamped system when it comes to usage in our designs. So we mostly, we use the overdamped system to see what happens if for some reason your zeta becomes greater than 1. So you need to have you need to have an analysis for that. But other than that, you want your operating systems, or you want your operating region for any control systems to be where your damping ratio is between 0 to 1. So that is an ideal operating region for any control designs. All right, good. So now that being said, I'm now here solving for my a, b, and c using the coefficients of my s square, s to the power of 1, and s to the power of 0. Good. So that is going to give me this a, b, and c in terms of s1 and s2. So what to be noticed here is I should have written it as some other values, but this s1 and s2 are not the coefficients s square and s1. So don't get confused. Right? But looking at now, I feel like you may get confused with that. So don't get confused with that. So it's very simple. I'm just putting this S1 and S2 for simplicity, right? Because if I had written that long term, right, that long roots that I'm writing just now for you, it's gonna look much difficult and tedious in simplifying this. But when I introduce this in the last step, and now if you see, I'm doing this S1 and into S2, that is going to be like a plus b into a minus b, and that's going to give me my a square minus b square, and in this case that's going to come out to be omega n square. I know that because I can see that my first term will cancel out, and then my omega n square and other thing will also get cancelled out. So I'm just going to get my omega n square when I do this, and that is going to be equal to 1. So my a is equal to 1. See how simple it was when I was using this s1 and s2. Similarly, I can write my b and c in terms of my s1 and s2, and then I'll put in the roots after I get these coefficients, after I get this partial fraction terms, and then I'll simplify them. Then I take the inverse. So that is advisable in this in this big roots. In this equations where your roots are not so simple to express. In previous cases, the roots were simple, and it was very easy to do the partial fraction with the roots in the partial fraction. So here we have used substitution of variables. So we have used S1 and S2 for your roots, and then we are simplifying it in this manner. And that should help you in not making too many errors when you're doing these simultaneous simplification. So what I am seeing here is I am having next two set of equations, and in that I am putting the value of a to be 1, and then I want to eliminate one variable so that I stick with one variable, and then I compute that variable. So in order to do that, what I've done is I've taken the first equation and I multiplied it with S1. So when I am doing that, when I multiply my first equation with S1, I get the third equation written here, and then I am just subtracting these two, and that eliminates my CS1 minus CS1. Right, so the variable c is now eliminated, and then I'm left with other terms which include my variable b. And then simplifying it again, I'm getting my b is equal to s2 divided by s2 minus s1. Good. So that is my b, and now I can plug in the roots and I can even simplify it further. So that is the stage where I'm going to bring in my roots and do the simplification. Good. So I can do this. Just I wanted to show you that this is a method that we are following, and now I can do my c also, right? So I can take for my c to be 1, right? 1 plus b plus c equal to 0 means I can write my c to be minus 1 minus b. So that is what I'm writing here. Good. So I have my a, b, and c. Now let's plug in these roots and simplify it, and then see what we can do with the inverse, whether we can apply the inverse and we can take the inverse directly. Okay, so I know when I do my S2 minus S1, I'm going to still get some terms cancelled because they are the same with only a difference of plus and minus. So that's why I'm doing that S2 minus S1 at the denominator, and that is going to simplify. That's going to take care of few things. Okay, that's going to how things are going to simplify. Yes, so that is going to get cancelled, and I'm going to just get it to be S2 by 2 omega n, right? B is equal to S2 by 2 omega n root of zeta square minus 1. So you have to be careful which root you use as 1 and which root was S1 and S2, right? In the first slide, we have selected, we have given some variable, we have expressed my S1 to be 1 and S2, it can be either, that is, but whatever you are using there, that the same you have to use here, because if I replace my S2 and S1 at this stage, I'm going to get, instead of this 2 omega n root of zeta square minus 1, I'll be just getting it as 2 zeta omega n. So that is going to be different. So you have to be very careful in sticking to the same substitution that you had used at the beginning of your the beginning of the derivation, and put the same values here, and that should take care of few things for you. And I can directly substitute my S2 minus S1 here to be 2 omega n root of zeta square minus 1, and then I'm doing the simplification, and that's what I'm getting. So this is totally up to you. You can, you can in your exam you cannot show S1 and S2 as your final partial fraction coefficients B and C. So we have to put it in terms of zeta and omega n, because these are the two variables that are fixed with your system. So omega n is your natural frequency, and that's not going to change, and your zeta is greater than 1, and that is also not going to change, because when I say greater than 1, it can be any value from 1 to infinity, but that is not a bounded system. So there you have, you have a reason for your system to get unstable or to go out of stability. So I'm just going to say like it's greater than 1, but I'm going to stick to a value of 1.2. So it's greater than 1, but it's a fixed value. So whenever your zeta or the damping ratio is fixed for a value greater than 1, then all these things that we are doing could still give you a very stable system. Good. So now that is your B and C in terms of zeta and omega n, and that is the simplification you have to do, and then you don't have to further do it here. So the step response, I can write my CT to be, because I know there is a direct inverse existing for these fractions. My 1 by s is 1, s plus 1 is e to the power of minus s1t, and 1 by s plus s2 is e to the power of minus s2t. So I have these fractions, and then I'm just now putting these, I'm just keeping it as b and c, but I know my b is that and my c is this, and then I can do this s1 and s2. I know what it is. Now I can just plug in all the values. So in your expression, that's going to look like a big, that's going to be one big equation for you, and you can do that in your exams, and then you can leave it at that. So that is your step response for an overdamped system. You don't need any much oversimplification. You can you can just do that, and it is going to be a linear plus exponential system. So that is what it is, 1 plus e to the power of minus z1t, right, minus s1 and s2. So that's going to make your system a linear plus an exponential system. The response of that is going to have a certain region linear and some other region to be exponential. So coming to the next topic, I have not drawn, no, we are saying time response specification. So what I was going to say is I didn't draw that graph for you previously, so I'm just leaving it as as a homework for you guys. So the time response specification is the next topic, and that is, so what I've drawn here, can you tell me what I've drawn here is your underdamped system response, because that is the model response that we are using. So that is that is what we are basing all our systems on. So that is why I'm telling you that underdamped system is one that is most widely used. And also for our time response specification or the time response study, I'm using the response of your underdamped system. So we have seen the undamped system is sinusoidal. Your this critical damping is also, it is a linear plus constant, and then you have your underdamped system, which graph is shown here. And finally we just saw now the overdamped system, and I told you it's going to be linear plus exponential. So we are not interested in other three, we are only interested in your underdamped systems time response graph, and that is what we have here. And from these graphs I can specify some of the points, some of the values that are very that are very important from the system design point of view. So whenever I'm designing my control system, I can use these parameters, I can use these specifications, and tell that whether my system is adequate or not. So one of that is, what are they? Delay time, rise time, peak time, settling time, and peak overshoot. Good. So what are these? So my TD, my delay time, is your time taken for a system to reach the 50% of its maximum output. So let's call an ideal system, and we are looking at our maximum output of 1. So 1 is my maximum output. So the time it takes to reach 50% of that value is your delay time. So I want, so suppose my delay time is 5 seconds, I'm not happy with it. I can improve it, I can make it to 2 seconds, so which means my system is much faster now. So that is how you tune it. So you as you can, or if you say you have an F1 racing car, like it's there are plenty of tons of control systems in your F1 going on. So that is there you need a very quick response, or your delay time should be very small. So that is where you improve it and make it better. So your rise time is TR, and that is the time taken to reach the maximum output of 1. Then your TP is your time taken to reach the maximum peak greater than 1. So that is what is TP? Just take a look. So the TP is the value is greater than 1. So which means it's called as an overshoot, right? So it's sometimes your system is not, it just not goes, it doesn't go to 1 and just say like, okay, I've reached my maximum, I'm going to stop, because you're giving that system enough power or enough kind of energy, and it may sometimes go beyond that 1, and then it knows that, okay, I've gone beyond 1, now I have to correct myself. So there is a corrective feedback, and that feedback, or a negative feedback, right? The negative feedback is going to kick in, and that's going to change your values, and that is the oscillatory behavior. That oscillations continue till your output gets to a steady 1. So that is what my peak overshoot value is, and my settling time is the time where you get that settling. That oscillatory becomes a steady 1. That is your settling time. All right. So now let's look at the formulas for these things, because these formulas are all derived from your underdamped system time response. So the underdamped system time response is something we have derived in this lectures, in the previous to this lectures. So we are going to just write the formulas for time response. I'm going to tell you a little bit on how we get these formulas, but we can easily solve these formulas from that final step response derivation. So my rise time is given to be TR, and that is given by pi minus theta by omega d, and we know what's omega d, right? It is omega n into root of 1 minus zeta square, and my theta is tan inverse of root of 1 minus zeta square by zeta. So how you get that theta? From that right angled Pythagoras theorem. Now we have applied that Pythagoras theorem on the right angle triangle in our underdamped derivation. So I strongly suggest for this part you need to look at the previous lectures on the underdamped system, and there you see this sine of omega d tr plus theta. So we have derived this sine omega d t plus theta, and for my rise time I am just gonna substitute the argument of my sine to be 0. That omega d tr plus theta equal to pi, and that is giving my rise time. So next is my peak time when my output hits 1, and that is going to be pi by omega d, and my peak time is taken as the derivation of rise time. So when I do the d by dt of tr, I get my tp. Good. So that is my peak time. So this is how, these are the derivative steps, and it is very easy to show how we get these peak times. And because when I am differentiating omega d tr plus theta, my theta vanishes, because that is not there is a phase angle, there is not much in it, so it becomes 0. That is why my tp is just pi by omega d. Then my settling time is given by 3 by zeta omega n. And how do I get that 3 by zeta omega n? My zeta omega n is my time constant. So I'll just, these formulas mean something, but I'll just tell you what the settling time is when your peak, when your output hits a steady 1. So when your output hits a steady 1, that is your settling time. And at that steady 1, we are only we're interested in allowing a small percentage of these oscillations. So that small percentage is decided by this numerator, which is ln of percentage. So when I do my ln of 5%, natural logarithm of 5%, I'm going to get it as 3 by zeta omega n. But if the question says I can allow up to a 15%, I'm not, I'm not very keen on that part. I can allow more tolerance. Then you can put that ln of 15%. And your peak overshoot is given by exponential minus zeta pi by root of 1 minus zeta square. Alright, so these are the formulas, and these formulas come in handy when you get a numerical in your exams, and you do get a numerical on the time response specification. You either get it for finding the step response. So you get two questions. Normally you see two questions in your gate exams or in your service exams or in your any kind of entrance exams or your university exams. So the questions are going to be, the first is find the step response of a second order system, and second one is obtain the time response specification. So find your rise times, peak time, setting time, then delay time, right? So these are the times, and you just get a question on find all these for me, and that is what exactly we are going to do now. So we are going to take a numerical. So I have a numerical for you. I have taken this from one of the exams, previous exams, and the question is very simple. So there is a bunch of things mentioned in the question, followed by this figure, and then finally they have asked you to find your TR, TS, TP, and TD. Good. So what I'm going to do is, what do I do for the solution? Like always, first I get to my transfer function. My transfer function is given by C of S upon R of S, and that is going to be given as 16 by S into S plus 0.8 divided by 1 plus 16 by S into S plus 0.8. So I'm just plugging in these values. I know what is my G of S and I know what is my H of S. I've just plugged in these values, and then I'm going to simplify that denominator, and then I'm going to get a term in this manner, right? So I'm going to get something like this. So here, so I have K. So this is interesting. So which means right. I have my damping ratio given in the question. So I have not mentioned it in the question here, but it is actually sitting right there on the book. So that is how you get the value of K. So let's get to it. So now this is my transfer function, which is in the second order form, and my denominator is my characteristic polynomial, right? So comparing that with the standard polynomial of S square plus 2 zeta omega n S plus omega n square, I can write my omega n to be quickly 4. Now my 2 zeta omega n is 16k plus 0.8. So now I have two unknown variables in the same equation, but it is given in the question it to be an underdamped system. So an underdamped system of zeta equal to 0.5 will give me my value of k. So I can write my k to be, I think it will come out to be 3.2. Let us see. No, it's 3.2 by 16. So it's 0.2. So k is my 0.2. And then I have my C of S by R of S is equal to 16 by S square plus. Now I'll just plug in the value of k here. And then I'm going to get what? 16 into 0.2 is 3.2 plus 8. That's going to be 4S plus 16. All right, good. Now this is my equation. So now what do I need to do? I just have to find my TR, which is very easy. Pi minus theta by omega d. And I know all the things. If you look at the equations for all your time response, TR, TP, TS, TD, and MP, you need only two parameters, right? You need only two things to find all these time response specifications. What are they? Natural frequency and your zeta. See, so your entire time. So if you want to adjust these times, so let us say I am having a Formula 1 racing car, and then I know I am very particular about this rise time, peak time, settling time, and my delay time. So this is my racing car I'm talking about. So everything has to be like fast. So I can just easily use my natural frequencies. I can work with my omega n and zeta, and then pretty much I can get those values, that optimized values that I need. Right, my TR, TP, and TS can be tweaked for a system by using only my zeta and my omega n. I don't need anything else. I don't need those block diagrams. I don't need those values, right? I don't need those second order transfer functions and all those things. Those are important for the stability. Those are important because we're going to see next stability of a control system in terms of your transfer function. So it is needed for that purpose. We want to understand how the system performs. Yes, right, that is very important. But to set these values, so what is my rise time of the system, how long it takes to reach a 300 mile per hour maximum speed in 10 seconds. Okay, I bring it down to 5. So I can bring it down to 5 by just adjusting this zeta and omega n. That is not, no, that is not, but I'm just saying it is an example, but there are a lot more things to that. But here I can tell that much from my graph, and I'm writing this time response also for you. Thank you.